In the previous video, we looked at how the codecoder sent a data stream like this to the other device called the co-commander. In this video, we will look at how this device can determine the position of the train from that data stream. Welcome to the official Railmagic Insider series hosted by the founder of Railmagic. Today's topic: the future of train automation. And this is how Railmagic works. In this data stream, we see that it has passed 3 magnets. The magnets are fixed locations. It's a kind of the intersections you have in traditional computer control. The difference is, however, that the magnet doesn't have a unique identification, and therefore the distance between them are used to identify them. We see in this example that we have 3 magnets type. That is, the first one is an S, then an NL, and the last one is an N. S and N stands for south and north, and that comes from a round magnet like this one. This round magnet is placed directly onto the center of the track under the baseboard, and that is used for turnouts. The NL comes from a rectangular magnet, and that is placed to the side of the track at the center distance between 2 tracks, or a similar distance if you only have 1 track. This magnet has a north pole and a south pole, and for the engine driver, that could be you now, this magnet is on the left side and you will see the north pole. So when you have the name NL, it means that the magnet is a north pole on the left side on the track. The co-commander has a database with all the possible routes between magnets. So let's take an example. We here see a section of a layout. There are 2 turnouts with round magnets underneath named C and E. Also, 3 rectangular magnets create fixed locations for 4 tracks, named A, B, D, and F. Now we will create a diagram where magnets are colored and distances are proportional to the actual length. The color codes are shown in the upper right corner. We use this diagram to identify the last magnet. First, we take the measured data string. It was south 780 mm, north left 321 mm, and north. The last distance is not used to identify the magnet. We are going to check all fixed locations for a matching pattern. We have no information about the previous magnets for the fixed locations named A and B, so we will not check them. First out is therefore fixed location named C. When traveling toward the right, the train might have come from 2 locations, A and B. From the engine driver's perspective, the first magnet would have been a north pole on the right side when coming from location A, while it would have been a north pole on the left side when coming from location B. The diagrams are right aligned such that the last magnets are above each other. Here we have the first match because the green magnets are very close in position. This will give a score of 0.9, whereas a perfect match will give 1. But because the type of the last magnet does not match, the candidate will not be accepted. We do the same for the fixed locations named D, E, and F. We see that for location E, both diagrams give a score of 2.8. Because the type of the last magnet is correct, these candidates are accepted. It does not matter whether the train came from location A or B, because both diagrams say that the last magnet matches location E, and that is the identification we are looking for. So where is the train? Well, now we use the last reported distance in the data spring. The train is 176 millimeters after the fixed location, but that can actually be two different locations because of the turnout. Therefore, the co-commander determines whether the train is on the upper siding or the lower main line based on the state of the turnout. The co-commander will of course also check if the train could have been running toward the left side, but as shown, no high score is found. We now know where the train is, but what happens when it approaches a signal? Let's go back to the example. Let us look at it from the side. The train is traveling toward the right. Inside the locomotive is installed the code decoder. It is the code decoder that passed the last magnet 176 mm ago. When the code decoder was installed, you told the system that the length of the code decoder to the front of the locomotive was 100 mm. The system also knows that the signal named G is 570 mm after the magnet named F, and therefore the distance from the magnet named E to the signal is 980 mm. The distance to go is therefore 704 mm. The co-commander checks the deceleration profile to see which speed step the train is allowed to run at. If different from the current speed step, it will for instance send speed step 5 to the locomotive number 3. As the distance becomes smaller, the allowed speed step decreases until the train comes to a stop right in front of the signal. Because the remaining distance is calculated based on continuous updates from the code decoder, it is not necessary to slow the train down to a threshold speed. We observed from this example that the start of the deceleration depends on the deceleration profile. Different trains can have different profiles. Also, the current speed of the train affects where the deceleration starts, and that is unrelated to where the magnets and block sections are located. Let us also see what happens if wagons are in front of the locomotive. Because you can input the length of the wagons into the system, it can compensate for that. It simply subtracts the length from the distance to go. In this example, with 350 mm of wagons, the speed step would have been changed to step 3 instead of step 5, and in this way bring the train to a complete stop right where the wagons are in front of the signal. Some of the benefits are that the braking profile can be adjusted, for instance, when the load of the train is changed. It's also interesting to think about that for traditional computer control, you define where the braking should start, whereas for Railmagic, you actually define where it should end, and the system automatically calculates when it should start the braking for each train. Also, occupancy is not detected directly on the track. Therefore, you don't need resistors on the wheels to make a short between the rails, such that the computer can sense where the train is. Instead, it's based on the same principle as we saw in the example with the signal, so that the system knows where the front of the train is. In the same way, it can also calculate where the rear end of the train is, and from that information, it decides which blocks are occupied by the train. Another benefit is that the system keeps tracking the trains even when you run them manually. So when you have finished shunting, you can just activate the engine driver and the train will run automatically from there on. And also if you want to have automatic train control as the ATC security system, you can run the train manually, and if you pass a signal of danger, the system could make an emergency stop for you. And when a train enters a station, there can be speed restrictions that depend on which track it's going to. And when it leaves a speed restrictions, it doesn't increase the speed until the rear end of the train has left the restriction. So that is also something the engine driver will manage for you. Reality is moving forward. So prototypical railways are going from the block sections protected by signals to something called moving blocks. So if you want to prepare for the future, Railmagic is the solution, because we track the trains like prototypical railways and we can implement the same kind of solution. You now know how Railmagic works. In the next video, we will show it in action, so stay tuned for that.